In this episode, we look at infrastructure protection by focusing on where security controls sit, how environments are divided into zones, how attack surface is reduced, and why technology diversity can matter. Infrastructure is the foundation that supports users, applications, data, networks, and services. If that foundation is poorly arranged, even strong tools may not protect the right things at the right time. A firewall placed in the wrong path may miss important traffic. A monitoring tool placed where it cannot see key activity may provide false confidence. A sensitive server placed in the same zone as ordinary workstations may be exposed to risks it should never face. Good infrastructure protection is partly about choosing controls, but it is also about placing them with purpose. You are learning to ask where a control belongs, what it can see, what it can stop, and what happens if it fails. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. Device placement means deciding where network and security devices should sit in the environment. A device can only protect, inspect, filter, or monitor the traffic and systems it can actually reach. A firewall between the internet and an internal network can filter traffic entering from outside, but it may not see traffic moving between two internal systems. A monitoring sensor placed only at the edge may miss an attacker who has already entered and is moving laterally inside the environment. A load balancer placed in front of applications may improve availability and help distribute traffic, but it does not automatically protect every backend service unless the architecture routes traffic through it properly. Device placement is about matching a control's purpose to the path of risk. Before trusting any device, you should be able to explain what traffic passes through it and what traffic bypasses it. Firewalls are a common example because their value depends heavily on placement. A network firewall can filter traffic between zones, such as the internet and a public service area, or between user networks and server networks. If the firewall is placed only at the outer boundary, it may help block unwanted inbound traffic, but it may not prevent one compromised internal system from reaching another. Internal firewalls or segmentation controls may be needed between sensitive areas. A web application firewall, WAF, is usually placed in front of web applications, where it can inspect application requests and block certain kinds of suspicious behavior. If the WAF is bypassed because users can connect directly to the application server, its protection is weakened. The lesson is simple but important. A control that is not in the traffic path cannot enforce the rules you expect it to enforce. Monitoring devices also depend on placement. An intrusion detection system, IDS, watches activity and alerts when it sees something suspicious. An intrusion prevention system, IPS, can go further and block or interrupt certain activity. These tools need visibility into the right traffic. If they are placed where they only see internet traffic, they may miss internal misuse. If they are placed on a busy link without enough capacity, they may drop traffic or miss events. If encrypted traffic passes through them and they cannot inspect it, their view may be limited. Logging tools have a similar challenge. A security information and event management, SIEM, platform can help analyze events from many sources, but only if those sources send useful logs. Monitoring is not only buying a tool, it is designing visibility so the tool can observe the activity that matters. Security zones are areas of an environment grouped by trust level, function, sensitivity, or exposure. A common design separates public-facing systems, internal user systems, server networks, management networks, development environments, payment environments, cloud workloads, and highly sensitive data stores. Each zone should have a clear purpose and clear rules about what can enter, what can leave, and who can administer it. A public web server should not usually sit in the same zone as a payroll database. A guest wireless network should not have the same access as employee devices. A management network used by administrators should not be casually reachable from ordinary user workstations. Security zones help reduce chaos by making trust boundaries visible. They also make it easier to write rules, monitor behavior, and understand whether a system is in a place that matches its risk. A demilitarized zone, DMZ, is a traditional example of a security zone used for systems that must be reachable from less trusted networks while still being separated from the internal network. Public websites, external mail gateways, remote access portals, and similar services may be placed in a DMZ. The goal is not to make those systems unimportant. The goal is to recognize that internet-facing systems have more exposure, so they should not sit directly beside the most trusted internal assets. If a DMZ server is compromised, segmentation should limit what the attacker can reach next. The DMZ becomes a buffer area with carefully controlled paths inward. The rules should be narrow and intentional. A public service may need to reach a backend database, but that does not mean it should reach file shares, administrator workstations, identity servers, and every internal subnet. Segmentation is the method used to create and enforce security zones. It can be physical, logical, or both. Physical segmentation may use separate equipment, cabling, or facilities. Logical segmentation may use virtual local area networks, VLANs, firewall rules, cloud security groups, access control lists, software-defined networking, or identity-based controls. The purpose is to prevent unnecessary communication and limit the damage from compromise. A flat network, where many systems can freely talk to many other systems, gives attackers more room to move. A segmented environment forces traffic through controlled points where rules and monitoring can apply. Segmentation should reflect real business needs. If two systems do not need to communicate, the safer default is to block that path. If they do need to communicate, allow only the required protocol, direction, identity, and destination instead of opening a broad path. Attack surface means the set of places where an attacker can try to interact with, abuse, or compromise a system. This includes exposed services, open ports, login pages, remote access methods, application interfaces, cloud storage locations, administrative consoles, user devices, vendor connections, and even human processes. Reducing attack surface means removing or limiting what does not need to be exposed. A server should not run unnecessary services. A cloud storage location should not be public unless there is a clear reason and strong review. An administrative console should not be reachable from the entire internet. A test environment should not contain real sensitive data without proper controls. Attack surface reduction is not about hiding everything from legitimate users. It is about reducing unnecessary opportunity for attackers. Every exposed feature should have a purpose, an owner, and a control that matches its risk. Device placement and attack surface reduction often work together. If a sensitive management interface is placed on a restricted management network, the attack surface available to ordinary users and internet traffic becomes smaller. If a database is placed behind an application layer and cannot be reached directly from user workstations, attackers have fewer direct paths to it. If remote access is routed through a controlled access service with strong authentication and logging, the organization can avoid exposing many individual systems. Placement can also support safer administration. Administrative tools should be separated from normal browsing, email, and everyday user activity where possible. That separation reduces the chance that a compromised user device becomes a direct path to high-value infrastructure. Where a control sits can determine whether the attacker meets a locked door early, late, or not at all. Security zones also help with monitoring because they give you expectations. Traffic between two ordinary user devices may be unusual in some environments. Traffic from a public web server to a payroll database may be suspicious if that path is not part of the approved design. Traffic from a guest network to an internal server should usually be blocked. When zones have clear rules, unexpected communication becomes easier to notice. Without zones, everything blends together and abnormal activity becomes harder to separate from normal activity. Monitoring at zone boundaries can show attempted policy violations, lateral movement, data transfer patterns, and misconfigured systems. This is why architecture and detection are connected. A well-designed boundary does more than block traffic. It also creates a useful observation point where defenders can understand how different parts of the environment interact. Technology diversity means using different technologies, vendors, platforms, or control types so that one weakness does not necessarily affect everything. Diversity can reduce the chance that a single vulnerability, misconfiguration, supply chain issue, or product failure compromises the entire environment. For example, an organization might avoid relying on one control type for every layer of defense. It might use endpoint protection, network filtering, identity controls, application controls, logging, and backup protections together. Diversity can also mean using different operating systems or providers in certain high-value areas. The benefit is resilience against common mode failure, where one flaw affects many systems at once. The trade-off is complexity. More diversity can mean more training, more integration work, more patching methods, more vendor management, and more opportunities for inconsistent configuration. Diversity helps when it is deliberate. Random tool sprawl usually makes security harder. You can think of diversity as a way to avoid putting every defense behind the same kind of lock. If every critical system uses the same platform, the same credentials, the same management tool, and the same network path, a single failure can become widespread. If different layers require different kinds of control, the attacker may have to solve several problems instead of one. This is defense in depth applied to infrastructure. A phishing-resistant authentication method, segmented network, limited administrative path, protected backup system, and monitored endpoint layer all support each other. If one control misses something, another may still slow or reveal the attack. The point is not to create complexity for its own sake. The point is to reduce dependence on one perfect control. No control is perfect, so architecture should assume that at least one layer may fail. Diversity must be balanced with operational reality. An organization that uses too many unrelated tools may struggle to configure, monitor, update, and troubleshoot them. A small team may be safer with a well-understood standard platform than with many products nobody fully understands. A larger organization may have the staff and process maturity to manage diverse technologies more effectively. The right level of diversity depends on risk, staffing, business impact, and support capability. You should also think about diversity across control types, not only vendor names. Two tools from different vendors may still fail in similar ways if they depend on the same identity provider, same network path, or same cloud account. Real resilience comes from understanding dependencies. A diverse architecture should be mapped, documented, and tested so the organization knows whether it has reduced common failure or simply added confusion. Infrastructure protection also requires reviewing placement and zones over time. Environments change. New applications are added, old exceptions remain, temporary access becomes permanent, cloud resources appear quickly, and business units adopt new tools. A design that was secure a year ago may become risky if no one maintains it. Firewall rules should be reviewed. Public exposure should be checked. Unused services should be removed. Zone membership should be validated. Management interfaces should be restricted. Monitoring coverage should be tested. Device placement should be reconsidered when traffic patterns change. Attack surface reduction is not a one-time cleanup. It is a regular discipline. The same is true for technology diversity. Tools and platforms should be evaluated for whether they still reduce risk, receive updates, have ownership, and fit the organization's operating model. Infrastructure protection is strongest when design choices are intentional and visible. Device placement decides what a control can protect, inspect, and enforce. Security zones group systems by trust, exposure, function, and sensitivity. Segmentation limits unnecessary communication and gives defenders useful boundaries. Attack surface reduction removes doors that do not need to be open. Technology diversity can reduce dependence on one platform or control as long as it does not create unmanaged complexity. The most useful habit is to keep asking how an attacker would move through the environment. What would they reach first? What would stop them? What would alert defenders? What could they bypass? What would happen if one control failed? When you ask those questions, infrastructure becomes more than equipment and diagrams. It becomes a security design that shapes what is possible, what is visible, and how far a problem can spread.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.